Hi, I'm Lucas. I'm a PhD student at the Technical University of Dresden in Germany, and I have a close collaboration with SAP. And today I'm going to talk about, we did a work where we benchmark persistent range indexes, and I'm going to talk about the lessons that we have learned in this work. So just to keep a bit of context, I come from a database background, so this might be a different background than some people. And why were you doing this work? So if you get in the past years, I did a quick Google Scholar search. The amount of works talking about non-volatile memory in these conferences I filter by ACM, IEEE, Usenix, and VLB. We see that cumulative amount of papers talking about non-volatile memory is increasing exponentially. So by 2018, we had about 12,000 papers talking about non-volatile memory. And I didn't have the time to read some of these papers, but if I sample based on when I started my PhD in 2016 and if I sample database conferences like SIGMOD and VLDB, 1/3% of the papers that talk about non-volatile memory, they are talking about, they are proposing some new sort of data structure. And in the context of database, they are mostly some variation of B+Tree. And what were the limitations of how this work so far? One of them is that the hardware is not widely available, so they're using either they're running their data structures and their benchmarks on DRAM, or they had some DRAM-based emulation platform where they can simulate higher latencies, and then we have one from Intel, HP, and I think the third one is also from Google at some point. Or they're using flash-backed DRAM devices, which ends up being more expensive. Third limitation is that since the hardware is not out yet, every work they were making different assumptions. So they were having different programming models. And also a problem that it happens in different works, not only in non-volatile memory or data structures, that every work they do evaluation, performance evaluation, but they use different benchmark methodologies. So it becomes harder to get the results of one paper and compare with the results of completely different paper. And then what we did is that we wrote this paper titled Evaluating Persistent Memory-Based Range Indexes. This is currently under submission. And this is a joint work with two colleagues from the Simon Fraser University in Canada. One of them is here, is going to present tomorrow, Tianzeng. And other two colleagues, Ismail and Thomas from SAP and Intel, both in Germany. And what is just to give an overview of this work, we picked 4 representatives of range index data structures that were proposed in the recent past. So the WB tree, the NV tree, the BZ tree, and the FP tree. And the idea is that this should cover a good amount of the design space, of the possible design space. So if we see here, we have like 2 data structures that they are completely, 2 trees that they are completely persistent, and we have 2 trees that are hybrid, so they combine DRAM and the persistent memory. They also have, most of them, they have unsorted, they use unsorted records in leaf nodes, but they do that in different ways. And in terms of concurrency, the WB tree is single-threaded, but all the other ones, they are multi-threaded, but they employ different concurrency mechanisms. So the NV tree is like uses a more traditional locking. The BZ tree is completely lock-free, and it uses this persistent multi-word compare and swap operation. And the FP tree, it has a selective concurrency scheme where it combines the hardware transactional memory with locking. So we got all these papers that were proposed in these past years. We re-implemented all of them using the PMDK programming model. And then we benchmarked them on real persistent memory. So we got access to the Intel Optane DC persistent memory modules. And what I want to talk next then is it's not so much go through the implementation details of these indexes, so of these data structures. The papers are here. You can go through them. It's like more high-level lessons that we have learned and things that we have noticed when doing this work. First lesson that I would like to talk about is that we should read and write as less bytes as possible per operation. And this is an obvious thing, like we have to do that even in DRAM. So why am I saying that? Is that, okay, it is obvious, but the thing is that most applications, they end up hitting other bottlenecks like network or NUMA latencies before they saturate the DRAM bandwidth. So if you get like a persistent data structure that you're using DRAM, and now you just want to use this on persistent memory, they are going to saturate the bandwidth much sooner. Here's an example. I've got one of the trees that I mentioned before, the FP tree, and we have the amount of the performance that we get for updates in this tree. And then you see, I cannot use this, yeah. And then you see that the performance, if you're running the FP tree on DRAM, it scales. After some point here, we start to have like, we start to go into this hyper-threading zone after 23 cores. And then even after that, we see that it's scaling much less, but it's still scaling. But if you're running this on persistent memory with two DIMMs and 6 DIMMs, or 3 channels and 6 channels, we see that the performance stops to scaling much sooner and the performance is much lower. So one thing is that, okay, is this just a matter of the latency, because persistent memory has a higher latency than DRAM, and it's not so much latency, but it's like the bandwidth is the villain, it's not so the latency. And this is something that other people have also noticed. So here I'm, just to exemplify that, I'm going to talk about the work of a colleague of mine. This is Georgios. He had a paper in the Daemon workshop a few weeks ago. It was collocated with Sigmod, and what he does is that he uses coroutines to hide memory, the latency of memory accesses. So in one of the experiments in this paper, what he does is that he has a sorted array. Here in the x-axis, we have different array sizes, and he's doing a binary search there. In the y-axis, we have the latency in terms of cycles per search. And this is a single-thread experiment. So if we see here in the baseline that we are interested, that is like the NVM one, this is the amount, the latency, the amount of time it takes to do this binary search in a 4 GB array. And when he applies this coroutine to hide the latency, we get like 5x lower latency for NVM. So this is a single-threaded experiment. So we see that, okay, we are successfully hiding the latency, but what happens if you go now to a multi-threaded scenario? And if a multi-threaded scenario here, we are in the x-axis, we are increasing the number of physical cores, and in the y-axis, we have the speed up that we get compared to the baseline, which is a single-threaded on DRAM. So we are interested to see these both lines here at the bottom. So the green one is the improvement that we get by using coroutines, and the black one at the bottom is the baseline running it completely on without coroutines, so single normal binary search. And you see that even though we have some improvement here, the performance at some point, with only a few cores, it hits this bandwidth barrier, and after that, we cannot go through. So the performance stays constant, even though we are increasing the number of cores. So this is, even we are hiding the latency, we hit the bandwidth barrier. And from this first lesson, we started to discuss, okay, what can you do to increase the bandwidth? An obvious option, it would be to, let's just have more DIMMs. We are running the experiments initially with 2 persistent memory DIMMs, and now let's say we could have 6. But the thing is that it's not so obvious. Would you always want to have as many DIMMs as you can? Not necessarily. So I say you have to carefully consider the use case before you decide for whatever setup is more suitable for you. So the DC persistent memory modules, they come in different sizes, so 128 gigabytes, 256, and 512 gigabytes. And then you have to make some questions for the use case that you want to build your server. How much persistent memory do you really need, and how many modules do you need? And here is just a mental exercise to make the case for that. Let's compare what would be having like 4 DIMMs of 128 gigabytes against having one single DIMM of 512. In terms of capacity, they are obviously the same. Having 4 DIMMs, it is much cheaper than having a single one. You also achieve a much higher bandwidth because you can use 4 channels instead of using a single one. But you are wasting here 4 slots. And if you're really latency critical, you want to have more DRAM in your system. So it might be, okay, I might want to have only 1 DIMM because then I have more extra slots that I could populate them with DRAM DIMMs. So a continuation of the second lesson is that, okay, also not all data structures that we have benchmarked, they present the same again. So you should not expect to buy just more persistent memory DIMMs and expect this to have a linear improvement or any improvement at all out of the box. So here we have a benchmark where we do a workload. So this is a fixed amount of threads, 23 threads. It's a uniform distribution of requests. And then we are comparing the performance of having this workload in a machine with 2 channels and 6 channels of persistent memory. So here we have all the 5 operations that our indexes have support. And then we have the 3 of the data structures that I mentioned before. And then the y-axis, we have the throughput that we achieve for each one of them. And then in the shaded area, where we say 2 channels, is the performance that we get with 2 channels. And these bar plots, they are not like stacked, they are overlaid on top of each other. So you see that we have 3 times the amount of channels. And for certain data structures, we get right away a linear improvement of 3x the throughput, which is an example here. But that's not for our operations. For example, if you see here the update, we are getting almost no improvement at all. And other data structures, you don't get this 3x improvement, you get a much smaller throughput. So this is not a trivial thing I mean, you have to consider that. It's not a trivial decision to be made. Third lesson that I would like to talk about is that for the time being, persistent memory should coexist peacefully with DRAM. So many people, they have raised the discussion is that, okay, persistent memory is never going to be widespread because it's too slow to replace DRAM or it's too expensive to replace flash. And the thing is that it doesn't have to replace one or the other, but there is a lot of potential for them to coexist peacefully. So there are many proposals for purely persistent data structures, and we picked 2 of them. A main advantage of those is that they allow you to have like instant recovery time. So you can recover them right away after a crash, and then we do a performance evaluation to say, okay, how does that compare, this recovery time compare against the hybrid data structures. So here we insert 50 million and 100 million records, and then we crash our index right away, and then you see how much time it takes now to open this index and start issuing requests again. So the 2 data structures, the 2 index structures to the right, they are fully persistent. So we can see that they right away, in the order of milliseconds, you can already start to use them again. And the other ones, the ones that are hybrid, we have to rebuild the transient data structure that we lost that was on DRAM, so we have to rebuild them. And then, of course, there is some penalty to be paid there in terms of recovery time. You get instant recovery time and potentially lower costs because you are fully relying on persistent memory and not so much on DRAM, but you have a lower performance. So here we see that the 2 for lookup operation, the 2 of the hybrid trees, they get a much higher throughput right away in comparison to the 2 ones that are fully persistent memory. And this is for a single-threaded scenario. If you go to multi-threaded, we see that even it scales much better, and even at a lower thread count over higher core count, we have a higher performance than the ones that are fully persistent. So we came up with these 3 lessons. And then we also, at the end of our work, we try to come up like what would be like a wish list, things that we'd like to have in future versions of the hardware. So we are really in an early stage. What would be the next steps as a way to give some feedback to the hardware community? So we came up with this wish list, and we said that, okay, for Christmas, or at some Christmas, not necessarily the next one, we'd like to have some things. Persistent caches would be a nice thing to have better performance, and of course, better performance is really generic. So just to be more precise here, because I mentioned before latency and bandwidth, I would like to have, if I had to choose, I'd say I would like to have better bandwidth. I mean, in terms of capacity is already quite okay. In terms of latency, it is much easier to hide latency in the software level, But in terms of bandwidth, we hit that bandwidth barrier, and it becomes really hard to get over it. And it would also be interesting to have more open source analysis tools that we can understand what's really going on the device level. So to see what would be the gains of having these things, so in the case persistent caches and better performance, we run a single-threaded benchmark, and we have 50% lookups, 25% inserts, and 25% updates, and have, again, a uniform key distribution. And then we want to see what's the throughput, again, that we have for that in each one of these trees. So in the red, we have like the normal baseline, the normal performance that we expect. And then we say, okay, what would happen if you have persistent caches? And how do we simulate persistent caches? If you have persistent caches, CPU caches eventually, what we can get rid of is this CL flush and CLWB instructions. So you don't have to flush anything anymore. If there is a failure, the caches are persistent, or there is some capacitor there or battery that's going to flush them. So what we did is that we commented all cache line instructions from our code. And then we see that we get some improvements, some performance improvements, not like life-changing, but it's still interesting. But a nice observation is that once we have persistent caches, we can completely get rid of all these cache line flush instructions and cache line write back. So that simplifies a little bit the programming model of persistent memory. We still need to guarantee that the stores are made in a specific order. So we still have to do this as fans whenever we are writing to persistent memory, but we could get rid of the cache line flushes. And then on top of that, we say that, okay, what would be to have how would it be to have better performance? And better performance here to be like a DRAM-like performance. What we do is then basically we run everything on DRAM to see how fast it would be. And then we see that we get a much better throughput. We have some nice improvements in terms of raw throughput performance. This is on top of persistent caches. So, so we still have the persistent, the S fancy, so we still have that barriers, but we don't have CL flush anymore.
That's the middle bar.
Yeah. Yeah, the blue bar is on top of that, so we still don't have this CL flushes anymore, but now we have like a DRAM-like performance. So, yeah, exactly, latency and bandwidth. So, what would happen if persistent memory was as fast as DRAM eventually? But we still need the fancies. And in this work, we are benchmarking this data structure. So we implemented like a benchmark framework, which we named now it's called PyBench, for Persistent Index Benchmark Framework. And so this is not something completely new, but we thought that this is a nice, framework, and we have some nice features, and it would be nice if to make it available for other people to use it and eventually start to contribute. So what are some of the nice aspects of this? That one of them is that the framework collects the metrics. We can specify a time window, and this allows a better understanding of the performance of the data structures. So it's not like you're getting the initial time, start time, and stop time, and then you divide how much time it took by the amount of operations that you executed, and you have the throughput. With that, you have like many time observations, and you can calculate the average throughput, for example, but you can also calculate the standard deviation, the variance, so you can understand better what's going on in between. So we integrated this with some hardware analysis tools. For now, is this processor counter monitor, which is open source, and also with ipmwatch, which we got access through Intel, and I'm not sure, eventually it should be open source in vTune.
I can't speak to the
yeah.
team, but I think the same counters are also exposed to public tools like emo or vTune.
Yeah.
So ipmwatch was really made for internal use.
But as long as the counters are available through vTune, you can integrate.
Counters are available.
Yeah.
vTune has a nicer public interface.
Yeah, so probably. We'd eventually, instead of integrating ipmwatch, would integrate it if we integrate
depending
between.
on how you benchmarking framework works,
Yeah.
I'd say EMO would be a better guess, but because it's more convenient.
Yeah. And at least the way it was, the way that we understand what's the difference between these two tools is that, okay, we are having our DRAM DIMMs and our persistent memory DIMMs, and the processor counter monitor is actually measuring the traffic that is happening between the CPU caches and the devices. And the ipmwatch is measuring the traffic that is happening actually between the buffer that's on persistent memory and the media itself. So the traffic here is happening in this granularity that was mentioned before earlier today of 256 bytes. Is that more or less correct?
It is correct for the current generation hardware.
Yeah.
Like Andy said, that might change in the future.
Yeah, for sure. So our framework makes like no assumptions about the persistent memory management. So I try to make it as modular as possible. So it doesn't mean it's only with PMDK. You can use any persistent memory management library. And the idea is that we have our framework, and all you'd have to do if you want to benchmark your persistent data structure, you just write a wrapper with an API that you define, and the framework just dispatches requests to this wrapper, and everything regarding persistency and the concurrency control that's left up to the data structure to implement. The framework doesn't care about it. So currently, it is available on GitHub in this URL. And like I mentioned, the idea is to have it low effort benchmark, so people can easily get their data structure. They can just write a wrapper around it and get all these benefits that I mentioned. So having this a better understanding of throughput and processor counter monitor, you see how much data, how many bytes are written and read from into DRAM and NVM. To conclude the talk, so I presented these 3 lessons. So you should read and write as less bytes as possible per operation, because the latency, it is higher than DRAM, but the problem really is the bandwidth. So we reach the bandwidth barrier very soon. Second lesson is that it's not obvious how many DIMMs you want to have and what's their capacity. You should really consider that based on your use case. Third one is that for the time being, we should leverage persistent memory together with DRAM for most, or at least for these more database-oriented use cases. In our wish list, then I mentioned that it would be nice to have eventually persistent caches. It facilitates the programming model, have a better performance, and if I would have to choose proof bandwidth first, the other things, it's easier for us to work around on the software level. And it would be interesting also to have more open source analysis tools or tools that allow us to understand what's really going on the device level. And that was it from my side. Thank you.
Great. Do we have any questions?
Yes, so you mentioned a paper from Ismail and Steve that talks about reducing the latency of the perceived latency of persistent memory. So that piqued my interest because I had a really difficult time actually hiding that latency. So can you speak a little bit more about that?
So it was you mean using the score routines to hide the latency? Well, I can speak, yeah. This one, right?
Yeah.
So another way, let's say a simpler way to show how to hide latency in the case of like a binary search. Let's say that you have your binary search, you're doing you're doing a binary search in your sorted array. And before you start to compare the element in the middle, you already know that you're going to have to access either the left element or the right element from this array. So you can already prefetch those before you do the comparison. So whenever you're going to access them, you're not going to have a miss. They're already prefetched.
Yeah.
So what you can do is that if you have multiple binary searches happening in parallel, you can kind of interleave them in such a way that you are always prefetching the next element before you need to access it. So this is a way of hiding the latency. You're not.
So this only works for
For sequential, what?
That have predictable workload. So if you have
Yeah.
enough data, then you don't
Yeah.
because this is just a smarter proprietary software.
Yeah, exactly. So you need to know exactly what you're going to access, and you must rely on the access pattern to do that. So it's not like a silver bullet that you can apply that anywhere. It's in specific algorithms and data structures. In the B3, for example, if you're comparing B3, you know that you have a subset of nodes that you can go, so you can prefetch them, for example.
Yeah. More cool. So I just wanted to mention that I have almost, well, maybe not the opposite, but I claim something different in my presentation. Because, in PMDK, we have experienced that it's often important to optimize even single cache misses to get to high latency.
Yes.
It's been because the PM latency is about 300 nanoseconds, and this really adds up if you have a very random workload. Right? So like you are in this graph right there, right? So the DRAM baseline is very low, and the biggest big line on the baseline for PM is due to this 200 nanoseconds on top of the latency, just adding up.
Yeah. And I mean, we can see here that you can also hide the latency of DRAM accesses of DRAM cache misses, but the improvement that you get with NVM is much higher because of the latency is, like you said, is higher. So
I want to make sure that mirror gets her full time. So you can answer another question while she's setting up, but I want to make sure that she
yes.